All right. Hello and welcome to Ask Me Anything About Video Signals with Andre J. Hi, I'm Andre J. This is a live ongoing series I'm doing for Polyphase Portal. Polyphase Portal is a new online-based version of sort of the phase-based thing that we were helping run in Brooklyn for a while. It's run by myself, Paloma Kopp, Sean Russell Hollowell, and Tim Caldwell. You can visit us at polyphaseportal.xyz and find out we do, in addition to these talks, we also do longer courses in learning how to work with analog video signals and digital video signals too. So yeah, check out our website. There's spots open for classes that are starting as soon as next week and going through the fall right now. Some pretty fun stuff. But about this series, I'll be answering questions submitted by you, the listeners, either in advance through the email, and you can find that information somewhere, or you can ask me the questions here live in the chat. You have to be, for those of you viewing on YouTube, find the link, head on over here to the Polyphase Portal version of this, and that's the only way I'll respond to your questions. Sorry, YouTube folks. But we like to use our servers better because they're less advertising ridden and spy wary. All right, so we're gonna start off with a question from last session. So we have a question from Kyle. Question is, I have a strange question for you about the Z-axis and how to convert a CRT TV into an XYZ display. How in-depth the project would be if it's possible. I have my X and Y deflection coils with inputs acting as an oscilloscope, and I talked to an old video engineer about getting the Z-axis information from the brightness. So, as is my wont, I don't know a really short way. Well, I could answer this in a really short way, but it would be not terribly useful. And a big part about what I'm trying to do with this series, at least in the starting, is like provide a really wide range of fundamentals of working with video signals. So what I want to do is use that question. I'm going to use that question as a starting point and talk about how does an oscilloscope work, how does a CRT television work, talk about vector and rasters a bit, talk about the mechanics of what's going on in there, and then by the time I get through all of that, the answers to that question will actually be pretty obvious, and the answers to a lot of other questions related to this thing will be pretty obvious too. So yeah, without further ado, let's talk about cathode ray tubes. So, a cathode ray is a stream of, hi Misty, a stream of electrons in a vacuum tube. So this technology goes back to the 1850s originally is when people started experimenting with shooting electrons from the end of a, so you have a cathode. Cathode is the negative end. Electrons get shot out and they want to go towards an anode, the positive end. So an electron is a negatively charged particle. People noticed when you have a vacuum tube or a tube with some sort of compressed rarefied gas inside, not just a regular old atmosphere, you shoot these electrons through and you get glowing stuff happening. So the first vacuum tube sort of cathode ray tube things used fluorescence in order to sort of like have something lighting up inside. And this is also the same sort of basic technology that neon tubes use. So a neon tube has a cathode and an anode, electrons go through, and then you have one of the noble gases in there, and the noble gas reacts to the electrons by fluorescing. Pretty sure that's correct. Please correct me in the chat if I'm saying anything ridiculous, because it's definitely going to happen. I am very good at speaking with extreme confidence about things that I probably shouldn't. For better or for worse, that's how it is. So I try to include this disclaimer as often as possible that I might seem a lot smarter than I am. Well, I definitely do seem a lot smarter than I am. I'm 100% confident that that is true. verifiable fact. So neon tubes, cathode ray tubes. So people figured out if you wanted to sort of like have more complex imagery being displayed and being controlled, you would have to use some kind of magnet to deflect the electrons. So originally you just have an electron going straight out, and depending on what kind of gas you have in there, maybe they'll like bump into gas molecules and like be sort of dispersed and heat things up and have just like a glowing cloud going on. But if you wanted to be, and some people would like put like a like some sort of like metal stencil into the tube, and then you would like see sort of the shadow of that metal stencil on the front. So that was sort of like one way people use these to display graphical information, but obviously a metal stencil is not a very complex image. So in order to have more complex images, people figured out two things. You want to be using magnets, some sort of magnet on the outside of the cathode ray in order to move and control where the electrons are going. And then you want to, instead of using fluorescence, you want to use phosphorescence. Phosphorescence is, so fluorescence is a property that when photons strike the substance, it glows. So that's, a lot of minerals have this. If you go to like sort of like geology museums or like fancy rock shops, they'll have these spots where like you take like a regular light or a UV light and you shine it on the stones and you'll see these glowing things. That's fluorescence. Phosphorescence is also mushrooms. Some fungus has fluorescent properties, and some other living creatures have this as well. So it's present in nature if you know where to look. Phosphorescence is a substance which has to be struck by an electron in order to emit light. So, so phosphor is just any kind of substance, and I probably should have done a bit more research on this exactly, where you have an electron hits it and then it will glow. It will actually emit light, and depending on the properties of that substance, it will emit light for a longer amount of time. So phosphor decay is something which is important when folks were building oscilloscopes and CRTs. You want to have a decay that is long enough for your purposes. So yeah, you need to use electrons. All right, that's a great question, Misty. I will get to that one at the end of this one in this episode, or possibly in the next one. You want to have some sort of electromagnet, actually, not just a regular magnet, because you want to be able to move things fast enough and with a really like minute enough control in order to have control over your image. And you want to have phosphors on the front of the screen. So oscilloscopes came first. Oscilloscopes were used before cathode ray televisions. And the way that an oscilloscope works, well, there's two kinds of basic ways that an oscilloscope works. There's the original sort of like prototypical way most people think of when you think of an oscilloscope. You think of sort of like this EEG monitor thing. We have like this horizontal line. So you have your electrons scanning in a specified rate, and usually you can control this rate, and they scan from left to right across the front of the phosphor-covered surface. And then you plug in some sort of voltage into some sort of, you have like a lead or some kind of like plug-in you can put your voltage into, and the voltage, positive and negative voltage, will displace that. So that's somewhat related to invert negative, or maybe not. That might be totally different. I should probably just read that question when I'm not in the middle of talking about something else. So that's sort of this time-based. You have a function. It's a function of time, and it's how does the voltage vary with respect to time. And then there is a secondary way in which oscilloscopes can display an image, and this is the way that most video folks, video artists are more interested in, is where you plug in two signals, and instead of scanning back and forth, your beam just stays stationary right in the middle of the display, and one of the signals will move it up and down in the Y direction, the other signal will move it left and right in the X direction, and if you've got your signals tuned correctly, they will draw like a continuous shape. in the X and Y direction. So the industrial use, the main usage of this that I'm aware of is for understanding phase relationships between signals. Say if you have two signals that are perfectly in phase, you will just have straight lines. If you have two signals which are 90 degrees out of phase, two sine waves, same frequency, 90 degrees out of phase, you will get a circle. If you have two square waves that are 90 degrees out of phase, you get a square. Two triangle waves, it'll be like a diamond. I forget what the sawtooth one is, but yeah. You can understand phase relationships, and you can also understand. It was actually we think about these Lissajous patterns as being like artistic things that we work with, but people would have a table of Lissajous patterns and sort of like how do they change with phase relationships over time, so you could analyze the ratio between two signals, because what Lissajous patterns really tell you from an engineer's point of view is what is the ratio of one signal to another, in terms of like, is it like when we think about harmony, we think about, is it a fifth above, is it a third above? These harmonic relationships are reflected in the frequency of the waveforms in respect to one another. So analyzing phase and analyzing frequency. And these are actually really useful things for anyone who's trying to understand how to generate Lissajous patterns from like the bottom up, not just using like sort of like existing sound to visualize it, but creating the sound waves themselves and then using that as visuals. All right. The other main use for this XY thing, which I think is really useful and isn't something that has been explored artistically that much, is you can use transducers. Transducer is something which will convert vibrations into voltage and vice versa, and hook those up to mechanical components and do things like analyze how do different parts of an engine run with respect to one another. So I can think of some pretty interesting ways that artists could use transducers, mechanical, like sort of old motors and engines, or just like the movement of people themselves in order to, or like people just shouting into it or stuff like that, or like a singing bowl or things like that in order to generate patterns on a screen. So transducers into an oscilloscope in order to analyze relationships between different components, mechanical or physical components. Oscilloscopes can work at many different rates. That's usually a feature that is like built into the oscilloscope itself, is what is its fastest possible rate. The fastest oscilloscope I had at the phase space would be like 50 megahertz, and that's pretty good for displaying like fairly complex XYZ patterns. Beyond Lissajous, doing like really complex sort of like shapes, you can feed it very high frequency, much more higher frequency than audio stuff. Most audio stuff you work with, the default is cut off at 44.1 or 48K. That's kilohertz. So megahertz bigger than kilohertz by an order of magnitude. But you need to have some sort of device that can actually generate sound waves at that. Either like really, I mean, not even really any high quality like sound cards are going to do that. Radio, like radio DACs, software defined radio, digital to analog converters are the only ones that can go up that high that I am aware of. The fastest analog oscilloscope, I just did a little research of this for fun, was 1 gigahertz. So that's even faster. That's order of magnitude up from the ones that I used. There's much faster. There's like hundreds of gigahertz speed digital oscilloscopes available now, or maybe they're digital analog hybrids. And these are used for people testing like satellite communication technologies. That's what that really high-speed stuff is good for. So the main difference between like the television, the way our cathode ray television works, and the cathode ray tube of a oscilloscope is that the oscilloscope just kind of moves directly with respect to your signal. The only sort of like thing that it generates itself is if you want this horizontal mode, the voltage over time mode, it will scan just back and forth in a line. It's not a very straight line. This is a better straight line. Just scans back and forth like that, and you have to like have it set to that mode in order to do that. On a television, it works in a different way where you start up here and it will just scan constantly going this way and this way. So you have these two electromagnetic coils, one of which will just like at fixed rates, these are fixed rates, pull the electrons starting from top left and going all the way to the bottom right. NTSC television, this does this 480 times, give or take. Some actually have more scan lines. If you have like PVMs, some PVMs would have a total of like 800 actual lines, so you just have line doubling going on, for better or for worse, depending on what kind of signal you're feeding into it. Some retro gamers get pretty upset when they're trying to run something that like was natively 240p, and using that with like one of those really nice Sony PVMs that has like 800 lines, and you look at it, it looks like ass because it's like 240p was already line doubling on a regular old consumer monitor, and you use this nice PVM and it's like line quadrupling. In addition to some other things that the PVMs actually kind of de-hance the signal. So kind of goes to show you that it's not always the case that more is better for every purpose. So that's a television. Television, you have fixed oscillators that just make the beam scan back and forth constantly. And this sort of brings us to like an interesting digression where we talk about what is the difference between raster versus vector. Anyone who's worked with like any sort of like digital image processing in their lives understands that there are vector image types and there are raster image types. And both of these image types, the origins of these, is that both of these kinds of displays were used for computers in order to display graphical interfaces. So the vector is the oscilloscope in an XY mode where you just have like these sort of like two one-dimensional signals that create this sort of like, it's not actually a two-dimensional signal, it is a line, it is a continuous line that is embedded in two-dimensional space, but the signal itself, if you have two one-dimensional signals, you do not get a two-dimensional signal. You just have a parameterized one-dimensional signal which is embedded in two-dimensional space. Maybe a little bit more on that later. And then a raster is where you have this sort of fixed scanning pattern where you're just always going to have like the movement there even if there's nothing actively being displayed. Like an oscilloscope in XY mode, if there's nothing plugged into it, it's just going to have a dot right here. And if you only have the Y thing plugged in, it's only going to move up and down. If you only have an X thing plugged in, it'll only move this way. So when people talk about like doing oscillographics with like a raster, they mean you're actually generating, you're using two saw waves to generate this sort of zigzag raster pattern that the hardwired electromagnets in the CRT would have. So raster just refers to like a grid. The bitmap is the canonical raster image type, and a bitmap is just literally like an array of values that says what's the value of the pixel here, just those numbers, pixel here, pixel here, pixel here. Another thing worth talking about when we're talking about rasters versus vectors is that a vector, especially this sort of oscilloscope style vector graphic, is more analog in one way of thinking than the raster, the CRT version. Because it doesn't really involve really sort of any encoding or decoding. And by encoding and decoding here, I don't necessarily mean like anything to do with like computer code or like ones and zeros or binary or anything. By encoding and decoding, I mean like information being like somehow like compressed in a way that needs to be decompressed when it comes out the other side. So like the signal that we plug in to like do vector things, it really just like takes that amplitude and converts that directly into how the beam moves. Whereas if we think about how television works, you have these sort of pulses in the signal. Even if we're just dealing with a black and white television signal, we have these pulses in the signal that talk about when a new frame starts and when a new line starts. So these things do need to have some sort of hardware involved to decode them. There's not a straight up analog one-to-one representation of how these things work. It sort of interrupts the continuously varying analog information with this digital pulse information that has to have some sort of decoding involved in it. And that's not even going into once you want to have color involved. So if you think about how an oscilloscope works with the vector graphics, it's really, if you wanted to have a color thing, the best way I could think of to do color with that sort of vector graphics is you'd have to have actually three sets of XY signals, three separate sets of XY signals, going out onto separate phosphor screens that would be R, G, and B, and then have some sort of projection or mirror-based convergence that brought them all together into one. So that would be something possibly interesting if somebody made like took like some old like black and white displays and then put like color films over them, set up the mirror, set up this like little stage show, do like one of those like Pepper's Ghosty kind of things, and do that with them. You could have like a color graphics, like a controllable color oscillographic thing happening. But you can see that it doesn't really scale up to color very well. Whereas in like CRTs, you have the ability to sort of like design them around so you could encode color in a sort of different analog way and have that be decoded by the hardware there. Let's see. Oh yeah, so vector is a parameterized one-dimensional line in two-dimensional space. Cannot do color terribly well. A raster is fully two-dimensional. And what I mean by that in fully two-dimensional is that like, so like if there's, let's say, there's like, imagine this was being drawn in vectors or being drawn on a CRT. So like this dark part, I'm very noir lit at the moment, so I've got a lot of extreme like contrast in my face here. On a CRT, or on a vector, say we were only turning this into like some sort of line-based raster thingy, you'd only really have to have drawing the image right here. Like say you just did like a topographical outline of my face and converted into like, use some Fourier analysis to like do the circles thing and draw like a squiggly spirograph outline of my face. You wouldn't need to have any information for this, and the beam of the oscilloscope would never go here because this is dark. This is not a part of the image. So vectors are a very compact way of storing graphical information because it's like, if you're not drawing something there, we don't even need to like know that that part of the image exists. In a raster and in a CRT, the line is the electrons are being shot out and being scanned with being drawn left and right constantly at a fixed rate. So this would still be, the beam would always scan here 60 times a second if this was a CRT television, but if it was a vectorized graphics display, it would never scan here. So vectors are sort of more compact in a way, which makes them very nice for certain purposes. So that's the sort of trade-offs. Can't really encode color information that well in vectors, and they do have to be a continuous line, and they are still sort of a two-dimensional image at heart, whereas a raster and a TV, where they're still a one-dimensional image at heart, rasters, two-dimensional, full array, have everything there, and you can do color in it. Alright, so that's rasters versus vectors. So let's talk about how people turn CRTs into oscilloscopes, or do sort of oscilloscopy style things with CRTs. First off, this is the disclaimer. Everyone must always say this when you ever talk about opening up a television or any sort of cathode ray device. You can kill yourself and kill people around you by doing this wrong. Don't do it if you have any sort of discomfort. If you're not completely comfortable with the way you've lived your life up until this point, don't recommend doing it. If you don't understand how grounding works, don't do it. If you are impulsive, sloppy, don't have a very well organized workspace, don't do it. Best thing to do is try to find your crazy, your crazy older friend or cousin or the neighbor who builds like Jacob's ladders or something like that. Someone who is comfortable and is experienced with working with incredibly high voltage things to, at the very least, stand by and like jump in and tap you to the ground if you're about to do something really dumb, like lick a flyback transformer. So yeah, you can die, kill other people around you. Heads up on that. Secondary disclaimer isn't really about like danger or anything, but it's just about complexity. If you're interested in doing this kind of stuff, and I'm not actually going to describe in detail how to do this. This is just a very vague description. You should look up tutorials and stuff like this and read documentation. That's much better than what I'm going to give you. But the broad spectrum thing I'm going to tell you is that you want to do this on a really old CRT. Something from if you can find something from the 60s or the 70s, that would be ideal. Just because the wiring is going to be a lot less complex. Also, there's a lot better chance that it's been sitting unplugged for like 20 years, meaning that the danger is possibly less than if you just opened up one that you've been using for 3 years straight. And using newer CRTs, you're going to have to do a bit more work in terms of like making sure that the signal is displayed, because there's just all of these sort of like power testing and like what do you call it, diagnostic components in newer CRTs that try to make sure that you've got like a pretty decent signal to display. So you don't want to just have something going blue screen all the time. Or worse, just not even like powering up the tube because it thinks that something isn't quite working in there and it doesn't want to power up the tube at all. So older CRTs are better. So if you want to use a CRT as a horizontal scanning scope where you just have voltage over time, you would open it up, being very careful, and you'd see that there's just like attached to the tube itself. There's is it? I don't know where it's attached actually. Don't quote me on this. I'm going to try not to talk out of my ass here. You want to desolder where the vertical deflection coil is attached. And if you'll see 4 cables attached. 2 of them are positive and negative for vertical deflection, and 2 of them are positive and negative for horizontal deflection. And if you don't know which is which, you don't have a manual, you just desolder one pair, turn it on, and you'll see either a horizontal line or a vertical line or a horizontal line. I can't remember which one. Vertical, horizontal. That's correct. So you remove the vertical one and you just get a horizontal scan, and you can just trial and error that. Just resolder the ones if you did the wrong one. And then you just, where you desoldered the deflection, that's where you just detached the electromagnets that would make it scan either this way or this way. Then you go in and you just solder a wire into there, bring it out, put a jack in there. And this is very simple and won't give you a very like high amplitude signal, but you can just plug a microphone or like an audio signal directly into that. And just keep a note that this isn't really making it an oscilloscope. It's not going to look as clean or as controllable as any oscilloscope does, because you're just sort of like hacking hardware, and that's how this stuff goes. And then if you want to do this in XY mode, then you desolder both sets of deflection coils, add 2 jacks in, and then use those 2 as inputs for your X and Y. And then you'll be able to draw leakage patterns. So the possible issues with this, so usually your horizontal and vertical rates are going to be limited. They're not going to be anywhere near as high as most oscilloscopes that you use for this. So you sort of have to keep in mind that, like, practically speaking, you can't really display a lot of high frequency audio forms, so you probably, anyone who's like interested in like, oh, I can do this mod and then I can set it up and like just do like the straight up Etra Scanimate style stuff, you're probably not going to be able to get a very like high resolution sharp version of that. You maybe have like a little itty bitty like Redetra thing, or a really coarsely drawn Scanimate Redetra thing, you're not going to have like the very like high def, very fine, high frequency version of that going on in these. So that's issue right there. Work out the math. I think horizontal scan rate is like 15 kilohertz. That's not very fast. That's not even up to like the highest audio that most people can hear. So, and that's something to keep in mind when you're doing this kind of stuff. You can do a lot of cool things about it. I'm not really going to talk about all of that. If you Google this, you will find Hackaday, you'll find James Connolly's stuff, you'll find all sorts of like interesting ways and like little things you can take off of. Once you start with doing this, there's cool things you can do with color. There's cool things you can do with all sorts of stuff. There's, yeah. Not even going to talk anymore about that. So, finally, I'm actually getting through this fairly quick here. So what is XYZ mode? So some oscilloscopes will have a Z input on the back. And this input is pretty much just like something you plug into. Usually if you have your X and your Y input on the front, you can also dial in sort of what's the like time base you want to work with, what is the, what kind of like amplitude are you scaling up and down to, so you can like have like a lot of control. You can, you know, is it AC, DC, whatever. Of course, you pretty much always want to be working with AC in these situations. But then you also have this Z input on the back, and the Z input you just plug something into, and it's got a fixed amplitude and a fixed rate. What you do with this Z, so the industrial use for this Z, all this Z does is change the brightness, the intensity of the beam whenever a signal is fed into Z. So the main usage you would have for this is if you're trying to like synchronize something to like a pulse, like this is for a lot of like logic-based systems, you're very concerned with synchronization of like sort of different mechanical or electromechanical things operating with respect to when a pulse hits. So you could use the Z input with a little like, what do you call it, a saw wave, and that would kick off like a pulse and make it very bright for a second, and you'd be able to sort of like see where on your line is this trigger hitting. So you use it to sort of figure out timing issues is the main usage for that. Now what people use when you have a Z input in, say, the like for like the oscillographics kind of stuff, what you use for this is you change the brightness, and by changing the brightness of like a part of your beam, you are able to sort of help create this illusion of depth. So say you're drawing like a line that's like, you've drawn like this sort of like three-dimensional cube thingy, but all of it's like all of the lines are like equal weight, then you're not really going to feel like anything's popping out at you, and you'll do that Necker cube thing where you're just looking back and forth, and you can see, depending on how you focus your eyes and how you choose to perceive the perspective at any point, you can see either one of the nearer, either the top or the bottom face as being closer or farther away from you. But if you accentuate one of those faces and then have like a sort of like gradient of brightness going to the back face, whichever one you want to be your back face, then it's very easy for you to look at that and see this illusion of depth. Of course, there's sort of an underlying concern here for people who are working, who typically think about how does XYZ work in terms of graphics and vectors, is that this Z is not controlling anything about the graphical information other than just the brightness, the combined brightness of your X and your Y. So when people actually wanted to make three-dimensional sort of images on oscillographics in these vector displays, you actually have to use multiple oscillators into the X and Y. So you're using, say, you have to have a minimum of 3 oscillators, and that's one oscillator for X, one oscillator for Y, and then another oscillator that is sort of controlling the sort of some sort of spatial displacement in X and Y that gives you this illusion of a three-dimensional image. So that's actually the underlying thing that you actually need for Z. I think a lot of people getting started with oscilloscope graphics get confused when you see a Z input on the back and you think the Z is going to kind of do this like Z displacement for you. The Z does not do that whatsoever. You have to do that on your own, feeding into the X and Y, because your vector display is not smart enough to do this sort of calculation of like Z displacement on its own. Something like Scanimate, which I think would be a pretty great topic for maybe the next one of these, did have like, it had an analog computer built as a front end that sort of was able to do X, Y, and Z, explicit X, Y, and Z modulation stuff, to the best of my knowledge. I should probably do a lot more research and make sure I'm not just like making up things that I dreamt about in terms of facts. So, if you want to be doing, so the simple answer, and this brings us all the way back to the actual question, the simple answer for if you want to have Z mode in your oscillographic modified CRT, all you would want to do is have like one more input, and that input doesn't go directly into the tube whatsoever. It goes into an amplification circuit of your X and Y signals first, and that will just sort of change the brightness, change the, actually no, that's not right either, because that's going to change the amplitude. So in order to change the brightness, you would have to sort of, change the, so originally, I'm actually not too sure about this one. I should have gone back and actually like, double check that I actually answered this question. Let's think about this for a second. So for a regular CRT signal, when you have the deflection coils already working, the amplitude of the voltage at a point was how bright it was. And then when you disable those deflection coils and you just plug your signals straight into the tube and you're doing the oscilloscope things, the amplitude is going to change your displacement. So you may have actually disabled your ability to do this sort of like amplitude to displacement thing. But I'm going to say maybe someone in the chat or maybe someone watching this can like comment or get back to us on this, and I'll do a little bit more research on actually what's going on, because I really dropped the ball here. But my hunch is that you can't really. I think you've just like set it up so you have fixed brightness at this point. And if you want to do actual sort of Z stuff, you could actually do what I said first, which is you have this Z oscillator which is tapped into your X and Y oscillator, and that will sort of help you draw more three-dimensional seeming images on the screen. But I don't think you're going to be able to do the Z brightness depth thing with this mod. I don't think so. You might be able to do other things like control like color displacement, where you have the R, G, and B things that get kind of like split off, where you add like little wobulators sort of things into it. There might be some more hacky ways to do that, and if I think about it real hard, probably not in a live scenario, I could probably have some tips for that as well. But I'm sure a lot of people watching this will have a lot of thoughts on what exactly is going on here. So yeah, that is, I think, what do you call it? XYZ displays, oscilloscopes, vectors, rasters, and CRTs, to the best of my knowledge, which might not be very well. All right, so Misty asks, what exactly is invert/negative in terms of analog circuits? Are they the same? How might one modify something like an old CCTV camera to produce or be switched to an inverted signal? All right, so an inverted signal, I should have brought some paper nearby. There might be some paper near me. So when you invert an analog, here's some paper, nice. So not even talking about any kind of video signal here. So we have that signal there. let me put this AC line in here so you see that it's going positive and negative. And actually, let me make this even easier for me to draw. Got that. So that's our signal right there. It's all positive. We invert that. It just flips it around negative. So that is an inversion of that signal. And if we invert the signal over here, then we would have it go like that. So that's an inversion of that. Mathematically, what we're doing is just like if your signal is S, then invert is just, and we always, for whatever reason, we want to scale our signals between 0 and 1. Not for whatever reason, it makes the math very easy. It's just 1 minus S. So that is one kind of inverting. There's other ways you can do it that use sort of like absolute values. So in terms of analog circuits doing that, I'm not the smartest one when it comes to actually doing mathematics with analog circuits, but I do know the things that you can do with so the operational amplifiers give you the operations of addition, subtraction, which is just inverted addition, and what do you call it? Multiplication and integration. So those are the things you can do. So technically speaking, if you understand how operational amplifiers work, how op-amp works, it's fairly simple to invert a signal. This would definitely be something that you'd want to take one of Sean Russell Hollowell's classes or Tim Caldwell's classes to get more information, because I could do some much better research and like explain the circuit to the best of my ability, but I don't think just talking about those circuits is the way to do it. I think actually working with someone who knows electronics much more than I do is the way to sort of learn and understand how to like work with op amps and signals like this. What I can tell you is how, so the second question is, how would someone modify something like an old CCTV cam to produce or be switched to an inverted signal? So I actually have had a number of like tube cameras, old school tube cameras from the 60s and 70s that have a switch that allows you to invert the signal. And my thing is always see how it's actually done, then understand the theory, and then try to figure out how to do it. Or see how it's done, reverse engineer that, and then try to figure out the theory from that. I would try to get my hands on one of those tube cameras that has a switch that inverts it, and actually just look at that and see how they do it in there. Because what I'm fairly positive, you have to figure out a way, so you want to, in your video signal, when you're working with it, if you have the fully encoded NTSC video signal, where you have the pulses, which are your horizontal and vertical sync, and then you also have all of this color information coded in there. You don't want to invert any of that information. You want to invert the luminance information, ideally. So you want to be able to get at your luminance signal on its own in order to just invert that. Or if you're working, so if you're working with like a smaller tube camera, in terms of like the ones that like aren't the giant broadcast ones that you'd have like, you know, big shoulder gear things to wear and everything. You have a smaller one, and those would actually interpret the signal directly. The sensors will be directly spitting out signals in terms of luminance, PB, and PR to start with, and that would give the ability to invert the luminance on its own, which would be the simplest before you have well, I think you actually have to have the pulses in there too. So I'm not quite sure how you work with inversion and pulses. This might be one that is looking into a little bit more. The other thing to think about is like on the big tube cameras, you would interpret the signal as RGB. So the light gets split into RGB, and then you have RG and B signals, individual ones being processed in there before it gets fed into the NTSC color encoder. So working with that would give you the ability to invert the signal. In terms of modifying CCTV cams, um, so I don't really know that many. So in terms of CCTV cams, most of the ones you're going to get your hands on are CMOS. So you're probably not going to have a fuck ton of luck modifying CMOS sensors, the image from that, in any sort of like really like obvious way, because there's so much DSP involved using proprietary chips and proprietary everything. The people who modify CMOS cameras, you can do some pretty crazy like witchy stuff, but it's hard to do the really intentional stuff. I just met Iowa City. I met Diego Video Sloth, and they seem like they've got a pretty great handle on like doing glitching a certain style of CMOS sensors on cameras. So maybe they have better information than I do on this. All I know is that modifying CMOS video signals is one of those things that it's very easy to fry things and not so easy to do intentional things. Stepping back one generation into CCD, the CCDs you might have a bit of luck with, but I'm not so sure. I don't personally have that much experience with a CCD camera that has an invert switch on it. And a lot of CCD cameras after a certain generation will also have some sort of digital biz working on the signals as well. So easiest thing to work on would be tube cameras because they will be the most forgiving to you in terms of you can mess around with the signal and not have it just die on you. But you're going to have to deal with the fact that tube cameras, if you buy one, I guess if you buy them, they're already kind of like about broken, so maybe you mess around with it, you know, fix it back and break it, so maybe that's a pro or a con. But yeah, the other thing to think about, so if we have our RG, there's different sort of ways of inverting a signal. So if we have RG and B as separate signals, like in those old Sony cameras, and you invert that, you get probably like what we think of as this sort of true inversion. It's not a channel-based inversion. You have the true image is inverted. This is something if you ever play around with like more complex image processing tools like the unfortunately named GIMP or Paint.net or Photoshop or anything, when you have the ability to invert an image, you see there's always like 5 to 10 to 20 different ways you can invert it. And they all do slightly different things, and it's pretty fun to take different image types and feed them in there and invert them and see how it does different kind of things. Because inverting a JPEG versus inverting a bitmap using different kinds of channel inverts are going to be kind of different things. And inverting like an RGB signal as opposed to inverting a YPBPR signal or inverting just the luminance part of a YPBPR signal is going to give you different things as well. And there's also different ways that people work with this because I think generally speaking your YPB and PR signals are all sort of like have like a DC offset in them. So inverting that, you also have to add something. You have to add an offset to get it back up to its regular area. That's something to consider. But yeah, much like with the last thing in terms of like how would you modify the brightness of a signal inside the CRT once you've turned it into an oscilloscope, this is one I think I'll do a little bit more research on and try to cover this one in the next episode. But yeah, I think that is about it for this session. If you have questions you want to be answered, read some text nearby this video and it will tell you how to submit questions. I think the next one will probably be in September because in the next month I will be even farther out of cellular service and network availability than I even am right now. But yeah, keep the questions coming because I'm hoping maybe in winter time I'll do like a more regular series of these every 2 weeks or something for a bit because these are pretty fun. All right. As usual, have fun. I hope this was useful information for everyone. And I'll see y'all's next time. And oh yeah, support Polyphase Portal on the Ko-Fi page. You're welcome, Misty. Cheers to you as well. Support Polyphase Portal via Ko-Fi if you like. You can support my Patreon if you like to. And yeah, see all y'all's in the future. You got it, Bar.